So today we are going to deal with this reaction diffusion equation. So this is with we consider the zero flux Neumann boundary conditions, and so the domain is 0, and so it's a toy model, and we want to see what's happening when the sigma is varied. So when we vary sigma, we want to see what's happening, and in order to get insights from this, we are going to treat the following exercise. And so in fact we already did the question 1 and question 2, and so we were working on question 3. So let's start with by writing our system again. So it's ut equals u minus v plus sigma u xx, and vt equals 3u minus 2v plus vxx. All right, so what we did last time is that we have our phi k, this is an orthonormal basis, and we have lambda k, and in fact lambda k it's pi square k square. And what we have is that so phi k xx equals minus lambda k, and also phi k prime. So this prime is with respect to the space variable at 0 equals phi k prime of 1 equals 0. So phi k satisfies the boundary condition. Okay, next. So I will replace u by is decomposition in the basis made with the phi k. So, and I write it like that. And the same for v. So basically what I want to do is I plug in these two expressions in the equation. So phi k, I know it. So I want to find uk and vk of t for each k. So if I do that, let me write the equation here, so we have it in mind. So u minus v plus 1x and vt plus 3u minus 2v plus vxx. So I plug it into that. So this is known, this works well. It converges and stuff. So we don't assume that there's no problem with that. So I just replace the u by the series here, and I take the derivative. So I obtain the sum over k of uk prime. So this is the derivative here is with respect to the time, equals the sum of also phi k uk phi k minus sum k and minus sigma the sum lambda k phi k. Because the derivative of phi, because phi k xx equals lambda k phi k. And I do the same for v. So k prime phi k equals 3 sum k minus 2 sum vk k minus sum lambda k. Oh, I forgot the uk here. uk and here vk phi k. So here and here I use the fact that phi k equals minus lambda k phi k. So phi k, when I take the derivative, is with respect to x, while the uk is with respect to t. All right, now I want, oh, how can I do? I would like from this to get rid of the sum over all the k's. I just want one fixed k. Can I do that? Can you do that? And how? How can I do that? Okay, so yes, no, how I do that? So let's multiply these equations by, let's say, phi and integrate. Between 0 and 1. So what do I get? If I do that, what will I get? So recall that phi k phi I equals 0 if I is not k, 1 if I is k. So if I multiply each equation by phi I and I integrate, I get exactly ui prime equals ui minus vi minus sigma lambda I ui, and vi prime equals 3 ui minus 2 vi minus sigma, no sigma, minus lambda I vi. And this is right. So once we have the system ek, so what the meaning of the question 4 would be that so the ek for ek large enough will not count so much. Between everything is going to 0, 0. So now you fix sigma and you try to prove that if k is large, meaning that that exists some k star such that for k greater than k star, 0, 0 is a sink for ek. So try to prove that. So our system ek writes uk prime equals uk minus vk minus sigma lambda k uk. This is for the first equation, and for the second equation, I have vk prime equals 3 uk minus 2 vk minus lambda k vk. All right, so let's call AK the matrix. So it's 1 minus sigma lambda k, here minus 1, here it's 3, and here it's minus 2 plus lambda k. So I'm going to have a look at the eigenvalues of this matrix. So I know that, let's call it mu k. So mu 1 to k. You know, it's 1 divided by 2, the trace of uk plus minus square root of trace ak square minus 4 determinant of ak. So it is worth to compute the trace. The trace of ak is minus 1 minus lambda k times sigma plus 2. So you can see that what's the sign of the trace of AK? It's negative. The trace of AK is always negative. As for the determinant of AK, we can write it in several ways. So for the purpose of this question, let's write it as, I will write it as sigma lambda k square minus or plus lambda k times, so I have 2 sigma here minus 1 here, and finally I have minus 2 plus 3, which is plus 1. So sigma is positive. So I have a polynomial with a positive value in front of the higher degree here, and so it's a polynomial of order 2. So it's positive if lambda k is large enough, this quantity is positive, and if this quantity is positive, then the two eigenvalues have a negative real part, because this is negative. And this is positive if k large enough. So from this, we deduce that 0 is the sink if K is large enough for sigma fixed. So now we proved that for fixed sigma, 0, 0 is a sink for our system EK if K is large enough. So, so the meaning of that is, so 0, 0 will be attractive. If I fix sigma, 0, 0 will be attractive for a lot of EKs. So in some cases, this will be sufficient to restrain, to limit our study to a finite numbers of EK. So it will be possible sometimes to grab the dynamical information from the whole PDE with only a finite number of ODE systems. So the next question is now to show that when I vary sigma, my parameter, there exists a value such that the EK, so 0, 0 goes from a sink to saddle node. So let's think about that. All right, so now we are giving the solution of the question 5. So it deals with what's going on when I vary sigma for the system EK. So I will so I add AK. So AK is given by this expression. So I will write it again here. So AK, we add AK equals, so I add here 1 minus sigma lambda K minus 1, and here 3 and minus 2 plus lambda K. So what I add again is the trace of AK is minus 1 minus lambda K sigma plus 1. And the determinant now, I will write it a little bit a different way, because I want to make appear sigma alone. So it's, I will get here, so 2 sigma lambda K. So sorry, I'll do it better. So it will be sigma lambda K times 2 plus lambda K, and the rest, so minus 2 plus lambda K plus 3, which gives sigma lambda K 2 plus lambda K minus 1 minus lambda K. So and as a reminder, the eigenvalues, so mu1 to k, are equal to 1 divided by 2, the trace of a plus minus square root of trace a square minus 4 determinant of ak. Okay, so if k is large enough, ek is a 0 is 0 is a thing for ek. But let's look at, so what's occurring is that, so if the determinant of ak is positive, the 0, 0 is a sink. Okay, this is a classical, right? Now, if the determinant of ak becomes negative, then I have a saddle. So I will just write now the condition that ak negative, and this is equivalent to sigma lambda k 2 plus lambda k minus 1 minus lambda k negative, which is equivalent to sigma less than so sorry, because it's a plus here, minus 2 plus 1. So it's minus 2 plus 3, it's plus. Okay. So sigma less than lambda k minus 1 divided by lambda k times 2 plus lambda k. Okay, so this is positive. So forget about k equals 0. Okay, k equals 0 is just the system without diffusion. So now if k is more than 1, the right hand side of the inequality is a positive number, and so when sigma becomes less than this one, the sink becomes a saddle point. All right, so you know that when you have a saddle, the stationary point for a two-dimensional ODE is no more stable, it becomes unstable. But so coming back to the exercise, so this is sigma k, all right? So sigma k is given by, so sigma k equals lambda k minus 1 divided by lambda k plus lambda k. Satisfies the claim of questions 5. Okay, that's interesting because for the ODE, we started last time with just an ODE. And for the ODE, we add a sink. And now I add diffusion. And so I add diffusion, so it becomes an infinite dimensional system. But usually diffusion stabilizes things. But in this case, if sigma is small enough, you have some positive eigenvalues that appear, which brings some instability. So the last question is just a simple computation, and so you get sigma 1, which is given by this value. So this is an important value because we will see that it changes the behavior of the PDE when you move sigma across this value sigma 1. Okay. So, so what did you see with this exercise? So first, that by using the Hilbert property of L2 of 0, 1, we were able to transform the reaction diffusion, the linear reaction diffusion system, into infinite numbers of two-dimensional ODEs. And for the specific for this specific linear system, we can see that when there exist some values of sigma such that when sigma crosses the value sigma k, we lose stability because the sinks become saddles, and so a stable point becomes unstable. So in fact, we proved this theorem. We proved this theorem. This was in question 5. Proposition 3 was in question 5. Here we proved that in question 5, and we proved the second claim in the question 4. Okay, so of course I told you that everything goes well. You can just plug in the infinite series into the PDE and everything works well. Well, you could prove that rigorously. Okay, so I let you that as an exercise. Next, so I invite you to think about that first. You can prove that sigma k is in fact decreasing. So you can prove that. So we are going to prove that. But this means that if sigma is less than sigma 1, then some of the ODEs, the solutions of the EK, so for some EKs, 0, 0 is a saddle for EK, which means that every single solution of the ODE, if you don't start in some very specific initial condition, will go to infinity because this is all linear. So you have to remind you what is a saddle. And this means that, in fact, the norm in L2 of the PDE goes to infinity. And this is for almost all initial conditions. While if sigma is greater than sigma 1, then UTVT goes to 0, 0 in the Banach space L2, L2 times L2. So we are going to study that the next few minutes, even hours.